Welcome to The Explainer. Today, we're taking a master's level dive into the fascinating shift of waste from an environmental burden to a highly valuable resource. We're going to walk through a comprehensive overview of Chapter 1 of the Manual for MENE 313, Energy Engineering, authored by your class instructor, Engineer Val Irvin F. Mabayo. We'll be synthesizing the absolute core concepts you need to deeply grasp as you tackle this material for the very first time. Here is our roadmap for today. We'll cover WTE as connected engineering problems, the circular economy, feedstock, conversion pathways, opportunities and risks, and finally, wrap up with an introductory engineering judgment framework. Let's jump right into Section 1, YT as connected engineering problems. It's really fascinating how this frames waste and energy. They aren't isolated issues at all. They are profoundly connected material flows. Think about it. Right now, 80% of the world's energy produced via combustion inherently creates gaseous waste, like carbon dioxide. Waste to energy, or WTE, forces us to completely flip our perspective. We have to stop treating waste like a magic disappearance act the moment it hits the landfill. Instead, we're moving toward an atom economy. Every molecule matters, treating waste as a tangible resource that we can actively recover. Moving right along to Section 2, the circular economy and waste hierarchy. In a traditional linear economy, the model is simple but pretty destructive. Take, make, use, and waste. Materials are permanently discarded. But a circular economy completely flips the script. Materials are kept in continuous use through strategies like recycling, reuse, repair, and material recovery. It's a closed loop. As we consider this flow, adapted from the Asian Development Bank, you can actually see how this works in practice. Unused waste potential, stuff that would normally just sit in the environment as pollution or take up space in a landfill mass, is instead actively redirected. Through smart, rational environmental management, it becomes secondary material resources and energy. Now, here's an absolutely crucial point you need to remember. Waste to energy has a very specific, strictly defined place within this framework. If we look at the expanded hierarchy of waste management, WT only steps onto the stage after reduction, recycling, and composting options are completely exhausted. It is the preferred solution for the residual fraction of municipal solid waste that just cannot be practically recycled. All right, let's head into Section 3, feedstock, which is really your starting point. Listen, if there's a 20% concept that explains 80% of this entire chapter, it is this right here. Feedstock is the specific waste material supplied to a conversion process. And here's the golden rule. Its characterization strictly dictates your viable technology choices. You literally must secure and rigorously characterize your waste stream before you select a technology, never the other way around. Simply put, if you don't know your waste, you cannot engineer a solution. So we immediately classify waste by its physical state, solid, liquid, or gas. Why? Well, it's a vital first step. Because a solid, like municipal solid waste or rice husk, is going to demand radically different handling, metering, and conversion strategies compared to a liquid, like palm oil mill effluent or sewage sludge. It's like they're comparing apples and oranges. The introductory implications for waste to E are tied directly to these categories. Let's say you have a highly segregated wet food waste stream. That immediately points us toward biological routes. On the flip side, dry recyclables or agricultural residues are going to point us toward refuse-derived fuel or thermal routes. Essentially, the waste's physical and chemical properties make the initial engineering decisions for us, which brings us to Section 4, major WTE conversion pathways. Let's look at thermal WT, which is the most globally dominant method for residual municipal solid waste. The sequence makes perfect logical sense. First, we heat the waste to volatilize the moisture. Second, we combust those organic compounds. Third, we transfer that immense heat to steam. And finally, that steam drives a turbine to generate electricity. This entire sequence can actually shrink the physical volume of the waste by up to 90%, leaving behind ash that can often be beneficially repurposed for construction. Now, pay close attention to these distinctions because this is definitely highly testable material. The major pathways are clearly separated by their process environments. Thermal pathways need combustible, relatively dry waste to produce heat or syngas. Biological pathways need biodegradable wet waste to produce biogas or digestate. And chemical pathways generally require highly homogeneous organic feedstocks to produce liquid fuels. You absolutely cannot mix these up without risking total system failure. And we can map specific technologies directly to their required feedstocks. Notice how thermochemical processes like torrefaction and gasification are paired right up with agricultural waste or refuse-derived fuel. Meanwhile, biochemical processes like fermentation and anaerobic digestion are perfectly matched with high-sugar organics and food waste. It's all about matching the specific tool to the specific material. Okay, let's shift to Section 5, Opportunities, Risks, and Safeguards. The opportunities here, like generating baseload power, massive volume reduction, and resource recovery, are undeniably huge. But we have to be realistic. The risks are equally significant. Air pollution from improper combustion, systemic failures from unexpected high-moisture waste, and a fundamental feedstock mismatch can financially ruin a project. So what are the required safeguards? You need strict, ongoing waste characterization, robust emission controls, and ironclad long-term secure supply contracts for your waste stream. Finally, we've reached Section 6, Introductory Engineering Judgment Framework. This brings us to a crucial quote straight from the manual. WTE is not automatically the best option for every waste stream. It is a highly powerful, transformative set of technologies for sure, but it is not a magic wand for all municipal failures. You'll definitely want to keep these critical takeaways in mind for your exams and future practical applications. They are the absolute pillars of sound engineering judgment. Number 1, characterization always comes before technology selection. Number 2, match the technology to the waste, never the waste to the technology. Number 3, you must secure long-term access and control of the waste stream. And number 4, always evaluate your options impartially against the circular economy hierarchy. I'll leave you with this final provocative thought to chew on for your coursework. As a master's level engineer, how will you rigorously characterize the true value and physical limitations of your next waste stream before committing to a conversion pathway? The next time you look at a landfill, don't just see a pile of garbage. Ask yourself how you will unlock its potential safely, efficiently, and responsibly. Thanks for joining me on this explainer, and I'll see you next time.